Welcome to a deep dive into the Laplace transform. To understand this, we shouldn't see it as a dry formula, but as a fundamental change of perspective. Imagine you are looking at a complex mess of gears, a differential equation in time. The Laplace transform is a magical lens. When held up, the gears become a simple list of numbers. The fundamental truth of this lecture is simple. Calculus is hard, algebra is easy. In the time domain, we deal with rates of change and messy integrals. These systems are described by linear constant coefficient ordinary differential equations. Solving them directly requires guessing solutions. But Laplace turns differentiation into multiplication by s. Before the math, we need to understand our measuring tool, the complex playground. A complex number s equals sigma plus j omega is just a point on a 2D plane. The star of the show is the complex exponential. E to the st, it breaks into two parts. E to the sigma t represents growth or decay, the magnitude. And e to the j omega t represents rotation. According to Euler's formula, this is a combination of cosine and sine. Combined, e to the st is a signal that is spiraling. It spirals outward if sigma is positive, inward if sigma is negative, or stays in a circle if sigma is 0. Now, the definition. The Laplace transform of f of t is the integral from 0 to infinity of f of t times e to the negative st. Think of this integral as a similarity check. We are checking how much our signal f of t contains the pattern of the spiraling probe e to the st. Let's calculate one. For f of t equals e to the t, we plug it in. The exponents combine to 1 minus s times t. Integrating gives us e to the 1 minus s times t over 1 minus s, but there's a catch. For this to converge at infinity, the real part of s must be greater than 1. Evaluating the limits, e to the negative infinity goes to 0 and e to the 0 is 1. We get f of s equals 1 over s minus 1. What about a constant signal, the unit step? Following the same logic, we find its transform is simply 1 over s. To transform a sinusoid like cosine omega t, we use Euler's identity to split it into two complex exponentials. Because Laplace is linear, we can transform them individually. Summing 1 over s minus j omega and 1 over s plus j omega, and finding a common denominator leads us to s over s squared plus omega squared. For powers of t, like t to the n, we use integration by parts. This creates a recurrence relation where each power of t adds an n over s factor. The impulse function delta t is an infinitely thin spike. Its transform is the simplest of all, just the number 1. Laplace also respects time scaling. If you speed up a signal by a, the frequency domain expands and softens by 1 over a. Multiplying by an exponential e to the t in time shifts our viewing window in the s domain. This is the s-shift property. A delay of t seconds in time creates a phase twist e to the negative st in frequency. The information is the same, just rotated. Now for the killer app, the derivative property. Using integration by parts, we find that the transform of f prime of t is sf of s minus the initial condition f of 0. Let's apply this to an RC circuit. Y prime plus y equals u, with y of 0 equals 0. We transform both sides into algebra. With a unit step input 1 over s, we solve for y of s using algebra. No calculus required yet. We use partial fraction expansion to break this into 1 over s and negative 1 over s plus 1. Looking these up in our table gives the solution. Y of t equals 1 minus e to the negative t. Integration in time is just as easy. It becomes division by s. This is derived by switching the order of integration in a 2D plane. Finally, convolution. This sliding and overlapping nightmare in the time domain becomes simple multiplication in the s domain. This duality is the heart of signal processing. Time is for dynamics, s is for state. By mastering these translations, you master the language of change.